These guys are part of a global race. It's been running for over a decade to build a mythical machine, the holy grail of calculations, a quantum computer. Remarkably, first-generation quantum computers have started to appear. Indeed, earlier this year, Google bought one, the D-Wave 2.
The promise of quantum computers is what would otherwise take you a billion years, you could do in a few seconds. And that's game-changing.
But as impressive as the D-Wave 2 is, it can only solve certain kinds of problems. The quantum computer these guys are working on potentially has very broad application, so the race is far from over. Conventional computers are built from silicon chips that have more than 1 billion miniature transistors etched on them. By cramming on ever more transistors, computers have been getting faster and faster. The problem is we can now squeeze so many components on a chip, we just can't get any more on. We're starting to reach the limits of that technology. Hence, the race to quantum.
Well, so quantum physics is really about the world of the very small. Things don't behave the way that we expect.
For example, an electron can be thought of as a kind of tiny magnet, but a magnet that points to the north and the south at the same time. Harnessing such mind-bending phenomena is what will give quantum computers their speed.
Well, so the quantum computer looks at all possible solutions at the same time and it gives you the right answer. So it works in parallel. So it's that parallelism that you just don't get with classical computer, which really has to go one after the other. So you're expected to get a much greater increase in computational power.
In classical computers, information is stored as strings of zeros and ones. They're called bits, and they're represented on the chip as tiny switches that are either off or on. But the switch equivalents in a quantum computer can be in two different states at once, on and off at the same time. They're called qubits. Research teams here at the University of New South Wales are working on a quantum computer based around a silicon chip with a single phosphorus atom embedded in it. A single electron from that atom serves as the qubit. A very impressive looking machine.
Yeah, so it's basically a scanning tunneling microscope. It's a piece of stainless steel with all the air sucked out from inside, so it's an ultra-high vacuum.
This machine is used to position the phosphorus atom in the silicon chip. But first, a single layer of hydrogen atoms must be added to the surface of the silicon. Then the microscope tip comes down. So you're going to physically knock off individual atoms with that tip?
Yeah, that's great. So that tip will literally, we use it to image the atoms, see where they are, and then we'll apply a pulse above each hydrogen atom and knock it off.
Yeah, it's
and
amazing.
Literally open up a hole of exactly 6 atoms to let that phosphorus in.
This is a world first.
We're the only group in the world that can do it, so it's really, you know, atomic kind of precision to get it in there. And we find that, you know, it never behaves the way we expect. And so you have that beautiful sense of trying to understand right at the atomic level what's really happening.
In this very sci-fi looking lab, another University of New South Wales team is fabricating other components needed by the quantum chip. Knights of the round table.
Indeed.
It's a clean room.
No dust particles allowed.
When you're working down at the atomic scale, a dust particle is like a boulder, so you have to be completely clean when you come in here.
Also, UV light interferes with the chip-making process, so the lights here have that yellowy colour because all the UV has been filtered out.
Around 100 labour-intensive steps are performed in here to build the chip. One of them is patterning a single electron transistor.
This is the chip, so that's actually had the tiny patterns where the metal will go to make the single electron transistor. This has used the electron beam with just a 2 nanometer spot size to write these tiny features.
Yeah,
and
it's tiny.
It's really tiny. And that transistor is the transistor that will read out the state of the spin on that atom.
This is the culmination of all that work in the clean room. And a wonderful little chip there mounted on a circuit board. It contains the qubit and transistor. The researchers have chosen a phosphorus atom to make their qubit because phosphorus has 1 extra electron compared to the surrounding silicon.
Now, that one electron that's attached to the phosphorus, like every electron, has what people call the spin. It doesn't mean it spins on itself. It's just an intrinsic quantum mechanical property. It's essentially a magnetic dipole. It's like the tiny needle of a compass.
To measure the spin, the chip containing the qubit is placed inside this superconducting magnet.
This large magnetic field gives a different energy to the two possible spin orientations.
And, in another world first, they can now detect and control the state of the phosphorus qubit in the silicon chip.
What you're looking at is in real time at, 1,000 times per second rate at the quantum measurement of a single electron spin in real time before your eyes.
That is amazing. So, I mean, an electron, a tiny, infinitesimally small thing, and we're measuring the spin
You're
on
just
that.
watching it on the computer screen. When the spike happens, it's because the electron has left the phosphorus atom. And that can only happen if the electron is pointing spin up.
However, the universal quantum computer these guys are developing still requires a lot of work. Which is why, over in Canada, D-Wave has adopted a very different type of machine.
The model that we chose is fundamentally more robust against environmental disturbance. It's simpler to realize on realistic timeframes for investors and all that to build something useful sooner.
This quantum computer works in a very different way. The D-Wave uses electrical circuits with superconducting currents running through them, which produce magnetic fields. The circuits behave like magnets and interact with each other.
Finding the minimum energy state of a lot of interacting quantum magnets, the mathematical structure of that is very similar to a lot of really hard problems. We've said, let's build a physical system that finds the answer to a problem physically. It's not changing the problem into a bunch of mathematical equations and solving it with digital logic. It literally is asking, what's the best arrangement of these spins, these interacting spins? It just evolves to that arrangement if we do it right.
But if it's a quantum computer, why is it so huge, I hear you ask?
That box is really to keep out electromagnetic radiation. It's like wrapping your radio in aluminum foil. You won't hear anything. So it's a big Faraday cage or shield. So, for instance, the chip down here, it has a cover on top of it, which is a radiation shield. This whole thing will be under vacuum, so there's no air molecules bounding into it.
D-Wave's fast and furious approach has meant they've actually got a saleable prototype out there. The drawback is its limited application.
It's not a general purpose quantum computer. It's application specific. If you're trying to minimize the risk of some financial portfolio, right, the mathematics is similar. If FedEx wants to find out of all the possible ways we could route our trucks, how do you do it to minimize fuel consumption? Those are all find the best of a vast number of possible solutions.
These are all examples of optimization problems. But of course, there are many other types of problems out there too. So, the race to build a universal quantum computer is still very much on, and these guys in Australia are front runners. When realised, the universal quantum computer will solve in seconds problems that a classical computer would have taken millennia to figure out.
We really want to build a kind of a universal large-scale quantum computer with error correction that can solve all the quantum algorithms that we know exist out there.
Solving known problems, like treating disease.
A very important one is to simulate the way that atoms and molecules are put together and connect, actually designing new types of molecules, perhaps drugs for the pharmaceutical industry.
And addressing problems we're yet to even discover.
We are making is such a completely different object that it's really hard to even imagine what it would be good for. The only purpose of telling you now what we think that's going to be used for is so that in 10 years from now I can listen to myself saying, oh, why did I say that? It was so blatantly wrong,